Welcome to Semiconductor News Decoded. I'm Ty, with 31 years inside the semiconductor industry, bringing you the real view from the factory floor. Today's topic? LSTC and IMEC have jointly cracked the puzzle of reliability variation in the wiring technology for the 1 nanometer generation and beyond. Today, we'll unpack what they found and why the tiniest variation in an invisible gap could decide whether a chip lives or dies.
As always, I'll explain everything in the most simplified way possible. Even a middle schooler should be able to follow along. If you're a specialist watching, some parts may feel oversimplified, but I'd like to prioritize giving everyone the big picture first. Think of it like making sausages. Stuff the meat into the skin unevenly, and the thinnest spot is exactly where it bursts first. So sit back and enjoy.
Here's today's news in one picture. It's a story about making sausages. We'll lean on this sausage analogy all the way through the opening section. A sausage is made by stuffing meat into a thin skin, the casing. But if you don't stuff it evenly, it bursts first wherever the skin is thinnest, or wherever the meat is packed unevenly. What decides the quality of the product is its single weakest spot. Now picture this a little further. Suppose you have a machine that makes huge quantities of these sausages automatically. At the center of the machine and out at the edges, the temperature and the pressure are subtly different, so the thickness of the skin and the firmness of the stuffing end up varying from place to place. When you make them one by hand, a craftsman can adjust each one. But once you're making tens of thousands, you have to control that variation across the whole machine at once. If there's even one spot that tends to come out too thin, that's where bursts will start to appear, one after another. And this isn't just a story about sausages. It's a challenge common to all of precision manufacturing. The principle that the single weakest spot decides the lifetime of the entire product applies exactly as it is to today's story about semiconductor wiring. So let's carry that idea over. From here, let me walk you through what this actually looks like in the real semiconductor industry. Now, let's get into the real explanation. What we're looking at today is a joint research result announced by LSTC, the Leading Edge Semiconductor Technology Center, a Japanese semiconductor technology development body, together with IMEC, one of the world's largest semiconductor research institutes, based in Belgium. The theme is ruthenium and air gap wiring. Ruthenium is a metallic element in the platinum group, drawing attention as a next-generation wiring material to replace the copper wiring that dominates today. When you make copper wiring extremely thin, electrons get scattered more easily at the surface of the wire and at the boundaries between crystal grains, which causes the apparent electrical resistance to rise sharply. So for the 1 nanometer generation, switching to ruthenium is being studied as a strong candidate. An air gap is a structure where you deliberately leave a gap of air between one wire and the next. Today, the space between wires is filled with an insulating material, the low-K film. But any insulating material has a higher dielectric constant than air, so it increases the capacitance between the wires. Air has the lowest dielectric constant of all, so using an air gap can dramatically cut the capacitance between wires, improving signal delay and power consumption. So what did this research actually reveal? What the LSTC and IMEC team uncovered is the variation in the TDDB characteristics of ruthenium and air gap wiring. TDDB stands for time-dependent dielectric breakdown, the time it takes for an insulating film to gradually degrade and finally fail as voltage is kept applied to it. It's a crucial metric for evaluating the lifetime of a product. The research team paid particular attention to is a phenomenon where the TDDB lifetime varies significantly depending on the position within the wafer. Between the center of the wafer and its outer edge, the processing conditions during manufacturing, temperature, pressure, gas flow, and so on, are subtly different, and they confirmed that this leads to variation in the width of the air gap. Why does variation in the width of the air gap connect so directly to lifetime? In an air gap structure, the narrowest part between one wire and the next, the minimum gap, becomes the weak point of the insulation. The electric field concentrates there easily, and that's where TDDB breakdown begins. The smaller the minimum gap, the shorter the lifetime. So controlling the air gap width uniformly across the entire wafer is essential to securing the reliability of the product. The reason this research matters for the 1 nanometer generation comes down to the shrinking of the wiring pitch. On today's most advanced processes, the wiring pitch has already entered the range of 10-something nanometers, but the 1 nanometer generation will require an extremely narrow pitch of just a few nanometers. The tighter the wiring pitch becomes, the thinner the air gap becomes too. So even a slight variation turns into a relatively large problem, and the difficulty of controlling that variation rises dramatically.
The approach of this research is also worth noting. Rather than simply reporting that this variation exists, it analyzes the physical factors behind why the variation arises depending on position within the wafer. The analysis method, which combines positional information inside the wafer with TDDB lifetime data, is practical knowledge that can be applied directly to improving the manufacturing process in the future. LSTC was originally established to strengthen the competitiveness of Japan's semiconductor industry. It's a research and development consortium that Rapidus and major materials makers also take part in, and it carries the role of developing the foundational technology for advanced processes at 2 nanometers and beyond. The joint research with IMEC is also meaningful from the standpoint of linking Japan's efforts to the global research ecosystem. Research into the reliability of wiring technology may look unglamorous, but it's actually a field that easily becomes the final bottleneck in bringing an advanced process into practical use. Even if you combine the two improvements of material choice, ruthenium, and structural ingenuity, the air gap, you still can't turn it into a product without controlling manufacturing variation. There's a huge wall between establishing the technology to form a wiring pitch at the nanometer level and forming it stably across the hundreds of millions of wires inside a chip. The phrase in the title of my personal take in the note article I've linked in the description, that a deliberate emptiness is what matters, is in my view the very essence of this technology. An air gap is a space with nothing in it, yet the shape and the uniformity of that empty space determine the lifetime of the product. The development of advanced wiring is turning from a competition over material technology alone into a competition over variation control and reliability design. This research from LSTC and IMEC uncovered the variation in TDDB lifetime of ruthenium and air gap wiring aimed at logic semiconductors for the 1 nanometer generation and beyond. They confirmed the mechanism. Slight shape variation during manufacturing, especially the difference in processing conditions between the center and the outer edge of the wafer, causes variation in the width of the air gap, and the dielectric breakdown begins at the minimum gap section. Ruthenium as a wiring material to replace copper, and the air gap as a means of lowering capacitance are each promising, but combining the two brings a new challenge into sharp focus, controlling the manufacturing variation. Let me wrap up. What this research shows is that simply changing the material or being clever about the structure is not enough to complete advanced wiring technology. Only when you can control the variation within the wafer across the entire manufacturing process and guarantee the reliability of the weakest section does it finally become a product. This is purely my own speculation, but since this is an announcement from a research institute, I personally suspect the results probably come from a wiring TEG, a test element group. If so, there's a real possibility that a particularly weak structure could later be discovered in an actual product, and it seems there are still plenty of research challenges remaining before mass production. I'll keep watching closely. That's all for today. I'll keep bringing you semiconductor news and analysis, so if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Ty on Semiconductor News Decoded.